Okay, so today I begin with a new chapter, random variables. Okay, so suppose this is a black box representing a random experiment. And so when we perform such a random experiment, there is an outcome omega. All right? And in many situations that we will recall some features of the outcome, okay, by using measurement devices. So it's possible that okay. And so each measurement device can extract one features out of from such outcome. Oh, I'm sorry. Outcome, okay. And so it is the device can be represented as the first one called x1, x2, etc., up to xn. Okay, and then very often the output, the result of the measurement device, number one, x equal x1, all right, and so we will denote as that an x1, the measurement device on the outcome omega, okay, and we get a value, and usually the value are numerical values, especially real numbers. Okay? For example, suppose the random experiment is to draw a student from NTHU campus, this main campus. So maybe there's some reporter want to have an interview with a student, means an NTHU student. So the reporter will come to the campus and randomly select a student, ask some of the questions. And all right, so you can think about the reporter draw a student, okay, and interview this student and ask us n questions. Okay, the first question would be what is your height? All right, so the height of the student, right? And so there is the value will be the height of this student interviewed. The second question would be, what is your weight, right? So the second value will be the weight of the students, etc. Okay, so there are quite a few questions to ask by the reporter to the students. Okay, and so this is quite often that so we usually record the features of an outcomes. Okay, and these features usually numerical features. So, alright, so I will describe that. So when a random experiment is performed, okay, we are usually or interest in some features or characteristics of the outcome. Instead of the outcome itself. And in many situations, okay, so in many situations, these characteristics can be expressed by real numbers. Okay. Examples. First one, in tossing a pair of dice. Okay, so we mentioned such an experiment before. So in tossing a pair of dice, we may be many interested in the sum of the two dice, or in flipping a coin n times. Okay, so in flipping a coin n times, we may be mainly interested in the number of heads, okay, that occur right. So we are mainly interested in just the number of heads that occurs. I'm sorry, the HEAD. Okay, sorry. Okay, so all these numerical values will be given special terms. So we say real valued random variable. So they will be called, right? So these values will be called random variables. Okay, so it's a function okay. Okay, it's a function from the sample space to R, to the set of all real numbers to the set R of real numbers. So X actually it's a function. And so for every sample omega in the sample space, just like here, okay, so x1 is a function, x2 is the number function, etc. So here we have n functions, and each function maps an outcome to a real value. Okay? So it's a function. So basically, it's a function from the sample space to the set of all real numbers. Okay? Subject to a certain general property. Okay, which will be discussed later. Okay, so any of these devices will give us a random variable. So random variable is just a function, okay, mathematically a function from the sample space to the set of our real numbers, because we will, especially in this semester, we are mainly talking about real valued random variables. Of course, you can have a complex value random variable. In that case, the codomain will be the set of all complex numbers. Okay, you may have arbitrary valued random variables. Okay, but well, we will focus on real valued random variable first. Okay. Any questions? And the important thing is that not just function. This function must subject to a certain general property. And we will discuss that property later. But just this moment, just a function, okay? All right, so let's take an example from, this is the 4.1.b. Random experiment. All right, so select 3 balls from the 20 balls in an urn numbered from 1 to 20. So in an urn, there are 20 balls, and the balls are numbered from 1 to 20. So ball 1, ball 2, ball 3, etc., up to ball 20. And we will select 3 balls from the 20 balls. Okay, so this is the running experiment. Okay, now, so the sample the sample space will be represented. So each outcome is just a subset, okay, of size 3. We call it ABC, and so you will see a subset of 3 integers in from 1 to 20. Okay. Now, so the size from chapter 1, the size is the 20 select 3. Okay. So is this combinatorial number? Okay, so the size of this sample space will be this one. All right, and because the sample space is a finite set, so the sigma algebra will be selected as the power set of the sample space. Okay, and the probability function is the counting measure. Is the counting probability measure on S, i.e. probability of okay for all outcome, yes. Okay, so that is simple. Now, we are asking that what is the probability that at least one of the 3 balls has a number greater than or equal to 17. Alright, so we ask for the probability of this event. Okay, so this is the event. Okay, the event. All right, so this is the code event, and it can be seen that this outcome 1, 10, 16 is not in this event. Okay, so if the the selected 3 ball is 1, 10, 16, then because the event says that at least one of the 3 balls has a number greater than equal to 17. Okay? But clearly, 2, 5, 18 is in E. Right? Because that one of the 3 balls has a number greater than, because the 18 is greater than or equal to 17. So this outcome is in E. But this outcome is not in E. Okay? Of course, you can answer this question, right, by using what you have learned in chapter 2, or maybe you can use some concept in chapter 3. But I think chapter 2 will be enough. Just enumerate all possible outcome in E, right? So if you know the size of E, then you know the probability of E, right? By counting measure, right? But okay, so that I believe you can solve this problem. Just take your time. Okay. Now I will describe another approach by using random variables. Okay. So we will define. So define a random variable. Define random variable means that we want to extract a feature or a characteristic which will help us to solve our problem. Okay, so what kind of the features we can extract from outcome like this one? When we look at this lot, we will see, oh, the largest number is 16, right? But 16 is less than 17, so of course, this outcome is not in the event. In here, we know the largest number is 18. All right, so 18 is greater than or equal to 17, so this outcome is in the event E. So we find a special characteristic of an outcome, which is what? Which is the maximum number, right? The maximum number the 3 balls have. So we will define a random variable x from the some space as to R as that for ABC, okay, this is defined to be the maxima of ABC, okay, for all in awesome space. Right? So now we take the feature or the characteristic that which describe the maximum of the maximum number the 3 balls has. Okay? So for example, x of 1, 10, 16, okay, x 16, x of 2, 5, 18, x 18, etc. So every outcome in the sum space, okay, has a value under this function x. Okay, and now we can describe this E. So now the event E can be described completely described as what? As that X as that E contains all the outcomes in a sum space such that X of omega, the function value, is greater than or equal to 17. Right? Because this feature enables us to describe the original event in a succinct manner, right? So E is here. And in probability theory, such an event will be denoted as X greater than or equal to 17. Says that random variable X is greater than or equal to 17. But remember, always remember, this notation means an event. Means that an event which says that this event contains all outcomes such that the function value, this outcome has function value greater than or equal to 17. Okay? Right? For example, we can define another random variable called y. And y is the minimum of the minimum number the three balls have. But this feature has nothing to do with our events, right? It cannot contribute anything, right? So the minimum number, you can define y to be another random variable, y to be the minimum number the three balls have. Well, but so there are other possible. For example, the sum of the sum of the numbers the three balls have. We call random variable z, right? So there are quite a few different characteristics that an outcome can have, right? But one of the features we call the maximum. We define the maximum, which is can be used to completely describe our original event E. Okay? Right, so in probability course, you have to gain such kind of experience to identify the right or the appropriate characteristics of an outcome, which will help you to solve your problem. Okay? Right? Now, all right, so this is, we use the random variable to describe the event. Okay, now, so now our job is to find the probability of this event. Right? But this event, this event can be decomposed into a smaller event that x is equal to 17 means that the three ball, the maximum number the three ball have is exactly 17. Okay? Disjoint union 18, disjoint union 19, disjoint union 20. Right? They must be disjoint, must be mutually exclusive. Okay. Okay, so, and by the countable additivity of probability function, the probability of this event is the sum of the probability of this event and probability of this event, probability of this event, as well as the probability of this event. Okay. So now we will say x is equal to I. This event is actually consists of outcomes in a sample space such that is equal to I. But this is the maxima, right? By our definition, the random value is the maximum of ABC is I. Right. So if the maximum of ABC is I, which means that I must be one of the ABC first. The second is the other two. The other two should be integers less than I. Why? Because ABC are three distinct integers between 1 and 20. Right? By our original set here. And so you can say that the size of, so from 1 is 0. Why? Because that you have three distinct integers here. The largest, the maximum one cannot be equal to 1, right? So this is 0. This is over 0, and x equal to 3, which is just 1, 2, 3. So it's equal to 1. Okay? And in general, the size is what? The size is that I minus 1 selected 2. Why? Because that because the biggest one should be I, because I is the maxima, right? So one of the ABC is I. Okay, and the other two should be less than or equal to I minus 1. So A and B should be selected from 1, 2, 3 up to I minus 1. Okay, so you have I minus 1 ball to select, right? And you have to select 2 out of from this I minus 1 ball. Is that clear? So that is the size. Is this one? Okay. So finally, the probability of the event, which is the probability of x greater than or equal to 17, it's the probability of x equal to 17 plus probability of x equal to 18 plus probability of x equal to 19 plus probability of x equal to 20. Right? So that is 16, select 2, and 20 select 3. 17 select 2, 20 select 3, plus 18 select 2, 20 select 3, plus 19 select 2, and 20 select 3. Okay. And the result would be 0.508. Okay. Questions? Okay, so for example, 1, 10, 16, this outcome is in x equal to 16. 2, 5, 18 is in x equal to 18. Okay, so because this is the biggest one, and so the other two should be selected from 1 to 17, right? 1 to 17. So that you have 17 ball, and you select 2 balls from the 17 ball. Okay, so this is like this one. Questions? Let's see another example, 4.1.c. Okay, so a random experiment. So independent trials of flipping a coin, and this coin having probability P of coming up head are performed. Okay. Continually performed. Okay, until either a head occur or a total of n flips is made. Okay, so there is a coin with two faces, head and tail, and you continuously tossing independent. You continuous toss this coin independently. Okay, and you will stop if there is a head to occur, or there already n flips are made. Okay, so at most you will make n flips. Now, what is the probability model for this running experiment? Okay, and I think you have construct the probability space for an independent trial, right? In last night, I think so. The quiz number 3. So X is the set of all sequences of heads and tails of length n. Okay, so you see that you may have H arrow okay, so you have, so in each in the sum space, each outcome is just a sequence of heads and tails of n of length n. So it's an can be represented by an n tuple, and in each component either an h or a tail. Sorry, not L. It's tail. I'm sorry. Okay. So you see the size is 2 to the nth power, right? It's clear, right? And the sigma algebra is this one. And suppose that the coin is fair, right? If the coin is fair, then, so if the coin is fair, so you can see that the probability for P is just the counting measure. So for every outcome, so for every atomic event, and it is equal to, so this is 2. This actually okay. All right, you have built that, and the counting measure basically we impose the independence on different trials. So that's why we have half, right? The half is from we have product, and the half because we have a fair coin. So the head and the tail will show up equally probable. Okay, so that's why we have 1/2, 1/2. Okay, and the product is from the independent trials. All right, so this is the probability model we have. We set up here for such a running experiment. But our game is really what? So we may Alright, so what? It's now we let x to denote. So let x denote the number of times the coin is flipped when stopped. So actually, we will stop flipping coin when either a head occurs or a total of n flips is made. So alright, so x goes to R, right? And for example, if the sequence, right, is this one, so the outcome is this sequence, and you see that the head appear at the first flip, so that the number of flipping is 1, because after one flip we stop, because an H, right, appears here. But for this one, all right, this is equal to 4, okay, because that you have to flip 4 times. Right? Suppose that the outcome is all tail. I'm sorry. I'm not sure. I don't know the reason why I always keep to write the tail as L. Okay. Right. So for this outcome, the face coming up are all tails, okay, and then we have n here, okay, because we have to stop, even though we have a tail shows up from the first flip up to the nth flip, okay, so etc. Okay, and from here, the possible values of x of this random variable, this function, are 1, 2, up to n. Okay? So you may ask that what is the probability that we will stop at the ice flip, okay? All right, but this is saying that the basic events, okay, which can be described by x are, right? So because now x, the possible values of x are 1, 2, 3 up to n. So the basic event you can be described by x will be x equal to 1. Okay, so it's the event that H is the result of the first flip. Okay? So x equal to 1 means that the head is a result of the first flip. X equal to 2 is that the event that L, H are the results of the first and second trials, respectively. Right? And up to x equal to n is that the event that the result of the first n minus 1 flips are all tail. Okay? Okay. Okay. So this event are the most basic event can be described by x. Because x has only n possible value there, probable values, right? 1, 2, 3, 4, 5 up to n. Okay, so x is equal to some particular integers from 1 to n, give us the most basic event. And the other events can be described by x will be actually the union of this event. So it can be seen that all events which can be described by x are unions of this basic event. Okay, for example, you can say x is greater than or equal to 3. Okay, so it means that at least you have to flip the 3 coins before stop. All right, so what is that? This is actually x equal to 3, disjoint union, x equal to 4, disjoint union, disjoint union, x equal to n. Okay? And okay, so this event will be so this n events will be called the atomic event. Can be described by X. Okay? Because and know that this disjoint union is it's the partition of the sum of space. Okay. Okay. Okay, so because we have described here, they are disjoint to each other, right? So I use that. I use disjoint union. And so their disjoint union is equal to a sum of space. Okay, so you have to differentiate atomic events okay, in the sigma algebra. The atomic event in the sigma algebra would be what? Would be all the singletons. Okay, the event contains only one outcome. Okay, so they are called atomic event in the sigma algebra. But when you refer to atomic event described by a random variable for this kind, you will see that the mass event equal to specific numerical value. Because there is no smaller event which can be described by a random variable like this one. Okay, so this is the basic building blocks. And all the events which can be described by X will be unions of these atomic events described by X. Okay? All right, so let's take a break for 5 minutes. Okay, so let's go back to our discussion. As I just say that these are events, atomic events described by x, by the random variable x. Yeah. So you can see that if you observe an outcome through a measurement, then some details will be hidden. Okay? Because you only see one feature, one characteristic of the outcome. But the outcome may have many different characteristics. Okay? Let's take the same example as sampling a student from NTHU campus. So if the question is about the height of a student, now if you know that the height of the student is 170, but there are so many students, right? Has height 170. Okay, so that the details, for example, the weight of the student may be different, even though they have the same height, 170. Right? So even though random variables is a very convenient tool, and is usually a very efficient way to answer your questions, but always remember, only one random variable, or even a handful of random variables, cannot completely describe the outcome of a random experiment. Okay? But in many practical situations, the data or the information we can have about a random experiment can only be obtained through measurement devices. Okay? Alright? So for example, if you have a disease in your body, medical examination give you distinctive features of this disease. An experienced doctor can only identify a handful of symptoms of your disease. So there is a risk for any diagnosis about your disease. Okay, the diagnosis may be wrong, and you may be mistreated and endanger your life. It's possible. Okay, because that there is no way, I mean, up to now, a perfect way to describe your disease, especially some complicated disease. Okay, so if you go to the NMR, you go to the CT or any biopsy, what you get only characteristics of your disease. And especially, they are expressible by numerical valued numbers. Okay, all right, and a good doctor or a good pathological physician will be able to give a diagnosis with as high as correct probability as possible for you. Okay? So usually, to see a doctor or to see a few doctors, to have different opinion. Okay, if your disease is complicated, that is reality. It's concerned to your health and your life. Okay, and everything, many things can be described in a probabilistic way. For example, in COVID-19, that if you give a shot of vaccine, you always be described that what is the probability for you to prevent from the infection? You can get only probability. Nobody can give you the deterministic answer. Okay, so another thing is statistical. This is we don't. This is the reality. This is the practice. Okay. All right. So many variables will play important roles, as you will see when we proceed in this semester. This is because that in many practice situations, only random variables can be observed, not the outcome itself. Okay? So the outcome will be hidden in our what is the black box. Okay. All right? Okay, so for a random variable x, the function defined by the probability measure okay, so defined. So this is a function, okay? It's called the cumulative distribution function. Okay, CDF of x. The CDF x of function from R to R. Okay, because that for every real variable x, now this is defined an event. Okay, so what is that? As we know, this is described an event which is omega in the sample space such that, okay, remember to convert this event into a subset of the sample space. Okay. Now there are two simple properties of a CDF f of x. The CDF of a random variable x. The first one is that the value of CF should be in between 0 and 1. Okay? This is because the probability function has value from 0 to 1. Right? So this is immediately from the probability function P. The second property is that if A is less than or equal to B, then the event x less than or equal to A is contained to the event x equal to B. So this event is bigger. This is bigger than that one. Okay? And so that f of A, which is probability of x equal to less than or equal to little a, will be less than or equal to probability of x less than or equal to b, because this event is bigger than this event. Okay, and this is f of b. Okay. So if a is less than b, then fa is less than or equal to fb. So which says that the CF is a non-decreasing function of x in R. So usually right? So now if we draw the picture of a figure of the CDF, and CDF is in between 0 and 1, so it should be confined in this strip, right? In this strip. And its monotone should be non-decreasing, so this should be in this way. Or maybe we have okay. So it may have jumped, but anyway, it should be non-decreasing. Okay. Questions about these two properties of OCF? Now we will describe the so for this, let's see the previous example. Okay, in this example, the probability x equal to 1. Okay, because they are atomic events, so we can compute their probabilities. So the probability that the tossing of a coin will stop after one toss will be half, right? Oh, by the way, I'm sorry. Oh, I'm sorry. I think this is incorrect. If half, okay? It's not p is half. Then it will be half, half, half. If it's p, then you can't have this trial. So if the coin is fair, but so when p equal to half, I'm sorry. Okay, so this is half, and p equal to 2 is that the first is the tail, and the second is the head, okay? And in general, n minus 1. Okay. So the first n minus 2 trials are all tails, but at the n minus 1 trial, the face is head. Okay. And finally, this means that the first n minus 1 trials are all tail. Okay, so this is this one. So this is 2 to the n minus 1's power. Etc. Okay, and so if we draw the CDF of this random variables, then we will see 1 and 2 and 3 up to n minus 1 up to n and plus 1. This is x. Alright. So we will have all zeros here. Okay. But and up to 0 we have this is 1. This is 1/2. And so we have a jump here. Because that if x is less than 1, if x is less than 1, so we see that we can say if x is less than 1, f of x, which is equal to probability of x less than or equal to x, is the probability of the NP set, which is 0, right? Because possible values of x are 1 and 2 and n. Okay, so that for x less than 1, the CDF, the value will be all 0. But up to, but at the 1, there is a jump. The reason is that when x equal to 1, you have half probability. So you get that. And then up to 2, and before 2, the probability, the CDF will remain constant. And then it will have a jump. So to this jump, the size is 1/2. Now, here, the jump is 1/4. Okay, and you will retain the same value. Okay, up to here. Okay, you go. Right, and from here, you go here up to, and then go to, it's 1. Okay, and the jump here is very small number. Okay, so you can see that it's a stepwise function. Okay, it's a stepwise function, and has jump at their possible values, 1 and 2 and 3, etc. Okay. So we draw here, circle here, and the jump size. Okay. So the last two jump size is 1/2 to the n-1 power. Okay, etc. So they are going up basically. So this is the CDF for this example. Any questions? Okay, so now we describe discrete random variables. Right. The first two examples, I mean, the previous two examples can have countable many values. For example, for this example here, the x has the possibility of x is 1, 2, up to n, so they are only n possible values. Okay, so they are what we will categorize such kind of random variables. So now a random variable. So later on, random variable will be abbreviated by r dot v dot. Okay, a random variable x that can take on one of at most a countable number of possible values is called discrete. Okay. That is X is a discrete random variable if and only if X equal to is the empty set for all X in R except a countable number of possible X. Okay, so that X equal to little x, this event is an empty set, except some countable number of possible X. All right. So for this example, the X can have a value 1, 2, 3, n. So that X is equal to for all okay. So this event must be the empty event. If the little x is not an integer from 1 to n. Okay, so these are called discrete random variables. Okay, now indeed an additional, remember at the beginning of today's lecture, when I define random variable, I say a random variable is a function from the sample space to the set of all real numbers, subject to a certain property, right? We will discuss later. So the same for discrete random variables. Okay, an additional, of course, it's a function from the sample space to the set. So with the range of X a countable set. Okay, so the range, if we describe the function, so the range is the set of all possible values of the function, right? And the range is a countable set. So now, but a discrete random variable need an additional condition. An additional condition should be imposed on a discrete random variable, which will be discussed shortly. Okay. All right. Now, before we discuss such an additional condition, we will describe what we will talk about a discrete random variable. So for a discrete random variable, we define the probability mass function of x as little px, defined to be the probability of x equal to little x for okay. The probability mass function describes that the probability of the atomic event, okay, described by x. All right. So remark. The basic event which can be described by a discrete random variable x are x equal to little xi for xi, for all x in the range of x. Okay. If we index the possible values of x by a countable say I, then the basic events can be denoted as okay. Okay, so that we usually, because the range is a countable set, so we can index the numbers we can index all the values in the values in the range by a countable set I. Okay, so the range will be denoted as xi and I in I. So capital I is just it's a countable set. For example, I can be from 1 to n, or the positive integer from 1 to n. Or I can be, so for example, okay, so I equal to the set of all positive integers. It means that I is 1, 2, 3, 4, 5, etc. And I is the set of all integers, positive, negative, and 0. I is all whole numbers, starting from 0, 0, 1, 2, 3, etc. Or I is just a set of 1, 2, 3 up to n. Okay, all these are countable set. So it can be used by to index the possible value of a discrete random variable. Okay, so that this is quite comprehensible. And this one is a little bit because that you have to know the range of it, because when x is the discrete random variable, by our definition, the range is a countable set, right? So that so x equal to eta x, when x is in the range, then this is the most basic event you can have. But another way to describe it would be by using a countable index set. Okay, so that this is a very common language to describe all possible values of a discrete random variable. Okay, and so so there are basic events, and all events which can be described by this discrete random variable x are unions of basic events. Okay, so yeah. Now it is clear that the disjoint union is a partition of x. Okay. Is a partition of the sample space. Okay, so it's a partition. And we would like to know the probability of each basic event for all independent set. Now we have to quote. We call them events. So if we want this to be events, they must be events of interest. Okay, so which implies that must be events of interest. And which means that omega must be in the sigma algebra. Because only the event to be an event of interest. I'm sorry. To be an event of interest, then we can assign probability on it. Because our probability function P is a function on the sigma algebra, right? So we assign probability for each event of interest. Means for each event selected into the sigma algebra. Okay. So if this event, these basic events are not in F, then we cannot assign probability. Okay. So now, what is this additional condition for a function, for a discrete function from the Summer space to the set of real numbers such that the range is countable set? What is this additional property? The additional condition is that all these basic events must be events of interest. Okay? Right? So they must be events of interest. Alright? In that case, this probability mass function will be well defined. So the probability mass function P of x is well defined. Okay. Any questions? Okay, in the game of archery, the score is 10, right? And then, right in the center disk, when the adder hit the center's disk, the score is 10. If the adder hit this part, the score we say is 8. Okay, and then it's 5 and 3 and 0. Okay. Suppose the player is blinded, for example, by masked their eyes, and just blinded, no training, right? So it's a running experiment. Okay, running experiment, and shoots at adder. Okay, so in here you have you can describe and P here. You can describe this random experiment by a probability space. Okay, and the X is the point. So you can describe the point by a Cartesian coordinate system. Okay? So you may think about, will be in some range. So you will say like minus b, rectangle. Okay, so the point the adder will hit, but described by a pair of real numbering between b and b. So you are modeling this property by, okay, so the sum space can be any point in this square. Okay, and F is the collection of events of interest. Okay, and the probability. The probability will be defined, can be defined to be the area of the sum space and the area of the event. Okay, you can define this one. Right, so A means the area, and the area of the sum spaces is 1, and the area of the event collected them. Okay. Now, X will be the sum space to R is the score. The point hit by the adder. Okay. And so the range of X would be 0, 3, 5, 8, and 10. So there are only 5 possible values. So X is the discrete random variable, of course. And then X equal to 10 is the center disk. Okay? So it's the center disk. And if we want to, so that the player will get score 10, if we know if that the point hit by the adder will be a point in the center disk. So that to assign probability for this event, then this subset should be in F. Okay, so it should be selected into this collection. And remember, any sigma algebra should satisfy logical structure. Okay, there are 3 axioms. One is that the total event should be in here. The second, if E is an event in the sigma algebra, then the complement of E must be also in the sigma algebra. And the third one is that if you have complement many events in the sigma, then their unit must be also in sigma algebra. That is the basic logical structure you should have. Okay, so you must select the sigma algebra that this event described by this random variable is an event of interest or is measurable. Okay, as we say, okay, i.e. measurable, as we said before. Measurable. Okay, so okay, all right. So I have to stop here. Okay.
P 就是一开始是 S。